Hi, and welcome to MSc. In this video, we're going to be looking at function transformations, and we're going to be looking at the combination of all the different transformations that we've seen so far. We're going to look at dilations, reflections, and translations. So we're really putting it all together. So this is a transform function g at x that is a function f at x that has had the works done to it. We see the a, k, d, and c values. So to recap, the a value is the vertical dilation, and it will vertically dilate it by a factor of a. If a is negative, then there'll be a reflection in the x-axis. This value must be distributed as needed, and we'll see that in the next example to clarify. The k value is the horizontal dilation, and it will occur by a factor of 1 over k. Again, inside the argument here of the function f, it's kind of opposite land. So if it's a large k, it'll be 1 over, and it will result in a compression. If k is negative here, we've previously seen that a negative inside will flip it in the y-axis. It'll be a horizontal reflection. This one must be common factored. As you can see, it is common factored here. Again, I will go over that in an example in a moment. The c value is the vertical translation, and it will be c units. If it's positive, it's up, and if it's negative, it's down. And the horizontal translation is d units. If d is positive, it'll shift right, and if d is negative, it will shift left. Remember the sign flip. So if it's x minus d, then the d value is actually positive. So here's an example of a standard function of the radical function, square root of x, and we are looking at a transformed function here, g at x, which is 3 times f bracket negative 2x plus 6 minus 1. This is everything. And we can see some of the things. I can see I have a number up front, a number in front of the x, and so on. So the first thing we have to note here is that I see brackets after my leading number that encompass the rest of the expression. And what that means is that this 3 needs to be distributed and multiply the function part here, the f at x part, as well as the constant number on the end. So what that means is this would look like 3f 2x plus 6 minus 3. And you can see how your apparent c value has changed because of this number out front, this a value, in fact. So that's what we mean by the a has to be distributed. We have to distribute the a value. The second piece was common factoring out that k value. So I see a number in front of the x. I need to common factor that out. And so we would write it like this, and we can use different brackets here. You can use square or rounded depending on your preference or what your teacher has told you they'd like you to do. And there you can see we've common factored the negative 2 out of just the terms inside the argument of f. So negative 2 times x is negative 2x. Negative 2 times negative 3 is positive 6. And then we have the 3 on the end. Notice here if we go to now talk about our a, k, d, and c values, if we hadn't distributed, I would have said my c value was negative 1. Now I'll say my c value is negative 3. If I hadn't common factored, I would have said my d value would be negative 6 because of opposite land. Now I'll say it's positive 3. The a value is the 3 out front, and the k value is this negative 2 that's there. Again, we would not have obtained the correct d and c values if we had not common factored and distributed first. When we go to list out the transformations, what I encourage my students to do is follow an acronym called DIRT. So this is the dilations, then the reflections, then the translations. That's the order that we should record it in. That's also the order that I should graph it in when I try to eventually graph this function. I find that's helpful, and the students often find that helpful as well. We always record the horizontal before the vertical in this process. So the first thing we'll do is we'll look for dilations. Well, I have both an a and k value, so I will start with my k value. I would say that I have a horizontal dilation by a factor of 1/2. Again, I'm only looking at the absolute value of k for the dilation, and its opposite land. K is 2, the dilation is a half. So I have this horizontal dilation by a factor of a half, and that's true because the absolute value of K is equal to 2. That's how we know. Now we move on to the vertical dilation. Well, I see a 3 out front. My A value is 3, which means I have a vertical dilation by a factor of 3. No opposite land there. And again, I know this is true because my A value, or more correctly, the absolute value of my A is 3. Turns out A is positive anyway, so the absolute value doesn't matter a ton there, but we're only looking at the size of the K and A to worry about the dilation piece. Then I move on to the reflection. I would start with the horizontal reflection first, and certainly that deals with the K, and the K is negative, so I do have a horizontal reflection. It's a reflection in the y-axis. And so we know this because K is negative, right? And that results in the reflection horizontally about the y-axis. We have no reflection in the x-axis because the A value is positive, so we don't need to list anything there. Then we move on to translation, the T part of the DIRT acronym. And that translation, we start horizontal as well. That's our D value, our D equals 3. And so that means that we are going to translate 3 units right. D is positive because it's negative here in the above expression. Once again, this is because the D is equal to positive 3 because of the opposite land inside here. That also resulted in the 1/2, remember. Lastly, we have this negative 3 kicking on the end. That's our C value, that's our vertical translation, and the negative tells me I'm going to go down 3 units. Okay? And again, I'll note that this is because the C value here is negative 3. So this is a complete representation of all the transformations that are happening to this parent function f at x, which is the radical function. If I were to try to write this out now, using the radical function, what that would look like, I would say that g at x is equal to 3 times, and then this part here inside the function goes inside the radical, and it's 2 bracket x minus 3 close bracket. The radical finishes, and outside is the negative 3 on the end. And that's my function g at x that has these transformations applied to f at x. When we go to try to graph this, it can be a tricky proposition because there's so much going on. Again, this is where students, I always encourage them to follow the DIRT acronym and start with the parent function, and as they're learning, apply one thing at a time. And as you get more skilled, then you can start applying multiple things at once. I'm going to use Desmos to help explain this. So here we have the radical function. This is my f at x function. First thing I apply in my DIRT acronym is the horizontal dilation. So that's the 2 that's here. Notice I've left the negative off for now. So what that does, if you recall, is it takes all of my x values and it's going to divide them by 2. So instead of it being 4, 2, it's going to be 2, 2 on this graph. Right? And you can see that's done all the way along for us here. Then we're going to apply our vertical dilation. I'll draw that here. So this is the vertical dilation. So not only now is it going to be 2, 2, but now we're going to vertically dilate by 3, which means it's actually going to become 2, 6, which you can see here. And again, I encourage them to do that for a couple of key points. And if they need to, sketch it out. Then we're going to move past the DI part of the DIRT acronym onto the R, the reflection. We only have reflection in one axis. We could have both in a scenario like this, but we only have one. It's the negative 2 here that's going to reflect it in the y-axis. And once you have this drawn out, reflecting it in the other axis is not as complex as you might think. Right? There it is. Then we can start applying the translations. Now, often students can apply both of these at once because we're shifting 3 to the right and 3 down. And usually they can shift 3 to the right and 3 down and do that on several points and draw it out. I've broken it up into 2 steps. There's my 3 to the right. Notice the x minus d. That negative 3 here is actually a positive d value, which shifts it to the right. And then lastly, 3 down. So this green curve here, that's our fully transformed function. Notice again that we had to distribute at the beginning and common factor. This is what we were kind of given at the start. And if I look at that, it will actually just go right on top of that other one. Those are equivalent functions. Okay? But notice we wouldn't easily be able to obtain my d and c value if I hadn't distributed and common factored. Jumping back over to our previous work, we can see that I've copied in our final transformed function g at x. So this is my g-axis here, this is my x-axis here. This graph then does continue on in this direction, but this is a terminal point. It doesn't go past that. And I wanted to look at the domain and range of this function as the last piece here. So x is an element of the real numbers, and there is a restriction on this, where x here has to be always less than this value, which is 3. So it always has to be less than 3. And in fact, it can also be equal to 3. And we can see that in here because we know under the radical, the radicand can't be less than 0. And so if I put a 3 in here, then that would make the radical, or the radicand, pardon me, be 0. If it was anything bigger than 3, then we would get a negative underneath the radicand, and it would be undefined. Notice this 3 here is related to this d value here. Looking at the range, we'll say that g, such that g is an element of the real numbers, where g always is greater than this value here. So it's always greater than negative 3, and in fact it could be equal to negative 3 as well. That comes from the fact that this can never be less than 0, because that would require that the radical value was a negative, and so this would be the negative 3. So this negative 3 here comes from our c values. And again, we start to see how translations can affect restrictions in functions. I hope that this overview of combinations of transformations has been helpful. If it has, please consider liking the video and subscribing to the station. And as always, thank you very much for listening and watching.